very much, Jonathan, for your kind introduction. I have to refute that. There's so many excellent researchers in this room, and I certainly needed that a broad base of researchers, practitioners, and companies work on this issue that is, turns out to be quite multifaceted. So where are we at this point? And I want to guide you through a few thoughts on my own. Some are very familiar to most of you. Hopefully something new is there that you find interesting. Certainly a few new research results. Is it a fad? Is it are we those who are interested in exploring this opportunity of biochar? Is it too much enthusiasm? Is it the next big evil? And Jonathan's cautious remarks are very much appreciated and a call to action. So we have maybe seen those. They've come and gone. The younger ones probably don't even know these guys, but they were in every household at some point, and we've long forgotten it. But we should dig out those old research and practitioner reports. I believe Helgi has made a presentation yesterday and has written about the early research. Mid-1800s showed a proliferation of research on biochar that is very interesting to go through, and it's hard to find, but I appreciate that more of us are looking into this because we can learn a lot from it. That research has largely ceased by the mid-20th century, and only in the last 10 years or more, rather in the last 5 years, we have seen a proliferation of research in this area. We should also remember that biochar is actually a type of material that's almost everywhere. We start to get a sense that black carbon, pyrogenic carbon residues from forest fires can probably be found in any soil and sediment to varying extents. Some only less than 1% of total carbon, but in many soils also more than 50% of the organic carbon is so-called pyrogenic or biochar type carbon. Notably, especially those soils that we treasure in the US the most, the Midwestern soils, seem to have more than 50% or around 50% of biochar type carbon, and one could argue that those soils are fertile as they are because of their large biochar type carbon contents. But I'll come with a key message that I will show at the end, right at the beginning, and everybody who has been following the biochar research in recent years has come to appreciate this fact that biochar doesn't equal biochar, to the extent that maybe we need to think about to not even use the singular of this term biochar anymore. And that can be so variable that it is almost useless to talk about biochar in singular. And biochar systems doesn't equal biochar system. They can be so different that it almost doesn't make sense to talk about the biochar system. And I'll give you some examples throughout this talk. But I want to start with a different area of research where I believe we have the same issue, and I want to make sure that we understand that biochar is, in that sense, also not singular. It is the same issue in other areas of science as well. And you see here from the TAG report that was headed by Duke University, who canvassed researchers, scientists, about scientific certainty, quote unquote, with respect to carbon sequestration and greenhouse gas emission balances. And the soil carbon content was judged with respect to the scientific certainty, for instance, through a switch to no-tillage. And you see that even with a scientific base of 250 peer-reviewed publications in the scientific literature about the effect of no-tillage on soil carbon in the US, the scientific certainty was only judged to be medium, and even lower with other measures to improve soil carbon contents for greenhouse gas emission management. So what is that all about? How many research results do we really need? 1,000 papers, 2,000? What's wrong with that? Actually, nothing's wrong with that. Maybe the question was the wrong one. Maybe the question was not understood correctly. Here is the average of the tons CO2 equivalents per hectare per year that those scientific results generated through a switch to no-tillage. And you see that the error bar is much larger than the average. Does that mean uncertainty? Does that mean we have no clue what's going on? Or does it rather mean variability? Does it mean it changes differently at one location, with one type of management, with one soil, with one crop, and differently in another situation? And I think that's what's going on. So it's not uncertainty, it's variability, and I would contest it's even predictable variability. So maybe the question was wrong. It was certainly understood the wrong way, and there was no correct question asked, so scientists had to vote for medium because what they actually saw was a variability and not uncertainty. So it's certainly, I think, not uncertainty, and I think that's also the fact for biochar becoming more and more the fact for biochar that we should not confuse variability with uncertainty. There will be many different biochars, and one biochar will do different things, and one biochar system will do different things than another. But that doesn't mean we are clueless. It's just different for different situations. And what we need is a box that contains all the knowledge and develops that knowledge system that we can predict and guide policy as well as implementation. Science certainly has exploded over the past few years. These are the number of peer-reviewed publications that are in ISI, the Web of Science, since the early 2000s. And with biochar or charcoal in the context of a soil amendment, and that has to be screened when you go through those. There's certainly a large body of scientific results on charcoal used for fuel. And you see that initially charcoal was of course the term used in that context, and since 2006 more and more biochar with respect to soil amendment. And you see that now there's about more than 200 publications per year are published probably in 2013 with the term biochar or charcoal in the title, and probably a lot more where biochar and charcoal is mentioned as one of the treatments, but not in the title. And you see that also, and that's the red dots here, that to benchmark that against other related scientific area, for instance compost, that at the moment more than 60% of the scientific activity in a very well-established field such as composting is occurring in biochar. So it's relevant. I think it's at a stage where the scientific activity is reassuring that over the next few years the scientific base and the knowledge base will be developed to provide adequate guidance. But we have to recognize that this is only happening right now. But the trend certainly goes in the right direction. I want to again make that point that there's a really important difference between the biochar as a material and the biochar as a system. And that evaluating biochar as a material is not sufficient to generate the benefits that is expected and to ensure that biochar is not the next foe, that we recognize biochar is a system, and it depends on a whole host of situations. A key property, and I want to stay with biochar as a material for a few slides before I go to biochar as a system, and a key property that triggers the interest of biochar as a material is its persistence in soil. There's no doubt about that, and that has ramifications not only for its use as a carbon sequestration tool, but also, of course, as a tool to improve soil fertility, because that ensures that biochar stays in the soil for a period of time that sets it apart from, say, compost, crop residues, or mulches. Some of the myths about the persistence, I think we should never say that biochar does not decompose. It does decompose. It does mineralize to a certain extent. Biochar in itself is not really stable, but what is, I believe, undoubtedly true is that biochars in plural can be produced that have a longevity, mean residence time of more than 1,000 years in a typical agricultural soil. But biochars can also be produced that have a very low persistence, a mean residence time of less than 100 years in a typical agricultural soil. And we need to understand which biochars and which soils have a long residence time and which have a short residence time. Key is to understand that charring, I believe, always leads to lower mineralization of the organic carbon from biomass. So the persistence increases through charring. And we know that a leaf will always, at one location, decompose more rapidly than a piece of wood. And the same is true for a charred leaf, will decompose less quickly than an uncharred leaf, and the same is true for a piece of wood. There are, and we know there are, fundamental changes in the chemistry of an organic material when it is charred. The original cellulose lignin structures are changed to more fully aromatic structures that are initially at lower temperatures, unordered and less fused, and they become more and more fused with higher temperatures and longer time, and that makes all the difference. Interestingly, when we looked at the published literature up to a few weeks ago from the 95 experiments in the peer-reviewed journal literature, we found incubation experiments that showed us mean residence times from 5 years to 8,800 years. So that's a huge, huge range. And we shouldn't be surprised by that range. And if I just pick out the lowest and the highest example here, the example of 5 years was a biochar made from bagasse at 350 degrees Celsius, which is a relatively low temperature for pyrolysis. It was incubated for 15 days, and only one measurement was made at the end to see how much biochar was there. And that, from that information, we were able to predict a mean residence time of 5 years. On the higher end, the biochar was made from grass at 650 degrees Celsius. It was incubated for over 3 years using multiple measurements over time. And that made all the difference in terms of how we can predict the mean residence time, as well as the stability or persistence of the material to begin with. So there are several different issues that are underlined here. There are differences in how these measurements were made, and there were differences in what the biochar was, the properties of the biochar. And here you see some of the methodological issues. On the left side, you see looking at the duration of experiments and the predicted mean residence time in a log scale. So this is 10 years, 100 years, 1,000 years, 10,000 years. And you see there's a vague trend that with longer duration of experiments, you get a longer mean residence time. And that's simply because there are fractions of the biochar that decompose relatively quickly, but they're a minor fraction. And if we do short observations of just weeks or months, we think that will go on. Whereas if we do longer experiments of several years, we get past that initial rapid mineralization and understand that after the first 1, 2, 3, 4, 5% of the biochar are gone over short periods of time, there's actually the rest of the material hangs in there for a much longer period of time. And if we can capture that, we can predict, I believe more accurately, the persistence of the bulk of the biochar. We also see that the measurements that are made with multiple CO2 measurements in dark here are generally above those where measurements were made only at a single measurement at the end of the experiment, or even with field-derived chars that fire-derived chars that were made in the field and where it is not possible to distinguish between erosion, leaching, and actual mineralization, actual return of CO2 to the environment. The methodological issue is shown here as well. For incubation, one incubation experiment lasting 5 years with multiple measurements. This is a result from, I think these are from Australian colleagues. And you see this rapid mineralization at the beginning, less than 0.2% were lost over a few weeks only, but then a slower mineralization over time. If we had only a one-pool model, so we had only captured one experimental term, we would predict a mean residence time of 966 years, with two pools, 1,600, and with the so-called infinite pool method, a ridiculously large number. So it's really important how this is done. Even with the same data set, you can do it in different ways. So you really have to read the fine print of how the assessments were done. And when titles of scientific publications read one way, then look under the hood and see how this was done. I think that's very important. The temperature at which we do our observations play a big role, and we know that bacteria and microorganisms are mineralizing much more rapidly at higher temperatures, but this change in temperature sensitivity is also different for different temperature ranges. And we see that very clearly that the so-called Q10, the difference in mineralization with a change of 10 degrees Celsius in ambient temperature is very different at lower mineralization temperatures, much greater that factor than at higher temperatures. And we need to understand that as well to firm up our predictions. And I think we've made great progress in understanding that. So it's undoubtedly that the difference in biochar material properties has something to do with its mineralization, and that biochars don't equal biochars for that particular question and for many others that I'll come to later. We've talked about that at higher temperatures, these aromatic, so-called aromatic rings, this here, they fuse together in more or less irregular sheets. This is a more idealized picture, but you can see that when we link these rings together, we have to kick out that hydrogen here. And that's what's shown here. So with greater aromaticity, when materials become more aromatic, have more of these refractory carbon molecules when they are linked together, they also have a lower atomic Hc ratio. So that is a way of gauging how well charred a material is and how aromatic a material is, which will help us in predicting the persistence of biochar in soil. And that's what's shown here for the currently available data set that satisfies our criteria of rigor in terms of the number of measurements that were made and the information provided. And you see that the so-called HC org ratio, the organic carbon ratio, relates reasonably well with the mean residence time. And that actually below a mean an HC org ratio of 0.48, we do consistently see a mean residence time above 1,000 years. That means of the so-called BC100 that we try to establish, that is the carbon in biochar that remains after 100 years, which is then important for possible carbon trading schemes, seems to be about 80% for a HCO ratio of 0.4 or lower. There is a large scatter still, as you can see, with HCO ratio. You can have either almost 10,000 years mean residence time or just a few hundred years. That doesn't seem to be explained in this data set by the properties of the char, but will have its reason in how the experiment was conducted, but also the soil type, moisture content, and other properties. So looking at just the properties of the char with HCORG as a proxy does not answer all questions, but it gives us a conservative measure of the persistence. But hopefully, eventually, we will be better than that we can have prediction models that include more than just the properties of the char. Marta Camps from New Zealand is advancing that to develop knowledge systems around that with a classification scheme, looking at the carbon storage value by recognizing this BC100, but also looking at the carbon content. So by multiplying the organic carbon with the BC100, looking at the stored BC100, and coming up with different classifications or grades of char. And we need those to be able to talk adequately about it, to not say biochar is this or that, because there can be a biochar in, according to this scheme, class 1, and it will be very different from class 5. So we need to have a better, greater nuance in our language to be able to communicate with each other and with the public and policymakers. Now a switch from the material to the climate impact, and I'll keep that brief because that's a huge topic, but reiterate that of course it's not just the biochar material properties, but there are all the inputs. What feedstock are we using? Are we growing it for the purpose of making biochar? Are we looking at the residues? What are we using? What else is produced in terms of energy carriers? What's avoided the decay of the biomass that we charred? The emissions, the avoided emissions, the energy, and then all the different greenhouse gases that are changed during the impact. And only if we recognize all of those, we will be able to adequately calculate net greenhouse gas emissions of the system. Here an example from Matthias' master's thesis, very simple and illustrative. Looking at the carbon remaining in an ecosystem, if we start at 100% and we have a tree that grows, we will have more tree after some time, possibly flattening out if it's not harvested. If we would char that tree, we would immediately return 50% of the CO2 to the atmosphere, arguably, possibly offsetting some fossil fuel use. But then the biochar may decompose much slower than the original biomass. So if we compare that to cutting down the tree and having the tree decompose, then we will have at some point a higher carbon residue with a biochar than with a decomposing biomass, and that will be different for very labile carbon sources versus very stable carbon sources. But the difference between these labile and stable carbon sources, that incurs a carbon debt during pyrolysis, because we are emitting CO2 right off the bat, and then again it's important to recognize whether that's offsetting fossil fuel or not, and that makes a big difference. But pretending it does not, then we're incurring a carbon debt that over some time will be compensated by a credit because the biochar decomposes slower than the original feedstock. And understanding that is important. Here you see for a 3-year incubation experiment the carbon depth credit ratio. If it's 1, then it didn't make any difference whether we charred or not for the carbon remaining. And you'll see that for some feedstocks and some temperatures, these are different temperatures for a given feedstock, higher temperatures on the right side and lower temperatures on the left side. And you see for some feedstocks we remain after 3 years still below a ratio of 1. For some feedstocks we are immediately above 1. So understanding the interaction between pyrolysis temperature and feedstock and the time required to reach that break-even point may seem important. That's important consideration. We know very little about the economic impacts and opportunities of a large-scale program on biochar, and the technical potential of biochar. This is from a World Bank report. Here I've just pulled out the Africa cropland scenario and the carbon abatement, CO2 abatement curves that have been done for many other technologies. And you see here that the marginal abatement costs. No tillage seems to have a very profitable, so a low number means here, a high negative number means there's a net return for the switch to no tillage, but you see the sliver is very, very small. It's highly profitable to switch to no tillage, but there's very little opportunity to do so. This is the biochar. There's a lot less profitable, but still net profitable to do it, and there's a lot more potential in terms of the total tons per megatons per year doing that for African cropland. And you see here alley cropping, intercropping, cover crops. This kind of information, this is of course very nascent, and I haven't looked into the details how the World Bank authors have calculated this, but we need this kind of analysis, and I haven't seen anything for the US or for any industrialized countries on this scale anywhere else. Switch now from greenhouse gases, persistence, and climate change mitigation potential to soil productivity. Soil productivity is really, for me personally, of course, it was the starting point why I was interested in that. I'm a faculty member teaching soil fertility, so I'm naturally closest to this topic. But also to realize the greenhouse gas abatement potential of a given biochar system, and to see a greater CO2 abatement with biochar than without biochar, there needs to be a soil fertility benefit. And that's difficult to provide firm guidance for all situations at this point. Here's from Simon Jeffrey from the Netherlands, Wageningen University, a meta-analysis already a couple of years old, but he's updating it at the moment. And you see changing crop productivity for all the reviewed papers at that time. The grand mean is somewhere around 12, 13. At the moment, I think it's shifting more towards 15 to 20 with the updated numbers. And then he unraveled the data sets to see what effect a change in pH of the soil made for the crop yield increases that were observed with biochar additions. And you see a clear trend here that if the biochar was not able to change the pH, there was no difference or very little difference to a control without biochar. But if the biochar was able to increase pH, change the pH significantly, there was more than 20% yield increase over overall reviewed studies. There's an inherent danger in looking at these data and interpreting them because there's so many differences here. And we know that, for instance, tea wants low pH. If we put a high pH biochar on tea in Kenya, we know that the yields go down and the quality goes down. If we put biochar with a high pH on a calcareous soil in Massachusetts, we know the yields go down. So looking at these data is instructive, but can be misleading if we don't look at the nuances. But we need a knowledge system because the knowledge is actually quite complex, and this is shows the effect of biochar applications on corn yields in a greenhouse experiment compared to a control. That's the dotted line. With different application rates, from low application to high application. Here shown only for 300 degrees Celsius and 4 different feedstocks, but in that study there were more information. And you see that we could improve crop productivity by a significant proportion or completely kill the plant in the process. But it always depended on all 3 investigated parameters. It depended on how much did we add, it depended on what temperature is what charred, and it depended on what we charred. And it was only one crop and one soil. So you can see the complexity of that, of choosing the right char for the right soil, the right crop, is not straightforward. But I would say it's not more complicated than managing fertilizers or composts. We just need to recognize that it's not a blanket recommendation, and I know that most of you are very well aware of that. My token example here is the pH. We can generate biochars that have a pH of less than 5, even lower than what's in this study. We can increase the pH with higher temperature, which is the direction this arrow goes in, and with different feedstocks, which is the arrow style. So we can either increase the pH or decrease the pH to the optimum soil pH range with the judicious choice of biochar. So we can tune the biochar properties to our specific needs, but we need to know both. We need to know what our biochar looks like, and we need to know what it is used for to make that recommendation. Very similar to fertilizer, by the way, or lime. So what we need is as a first step, we need a biochar classification that recognizes different soils, what it might be used for, the different biochars, and the different uses, because it will classification possibility, looking at the fertilizer value, which is something that needs to be recognized, but is probably not the parameter that most of us are interested in biochar for its fertilizer value. But attempting to look at the phosphorus, potassium, sulfur, and magnesium levels to classify biochars into different categories, to start not talking about biochar in singular, but biochar with certain attributes. Biochar class 4 fertilizer value will be completely different than biochar class 0 fertilizer. And that's what's what such a classification, for an example here that she calculated through, could look like, where you have carbon storage class that I introduced earlier, a fertilizer class, maybe a lining class, particle size, and suitability for soilless agriculture with different knowledge systems. So that those kind of classifications is the precondition to us moving anywhere further to understanding this better. But this is not sufficient, because we need then to provide guidance which classes to be used to which soil, which nobody has even started, to my knowledge, in earnest, to develop such a framework, although we've all thought about it and discussed it, I think. Another important issue is that before we even consider putting biochar on, whether it's suitable for one soil or the other, it needs to be safe to begin with. And the toxins are, of course, the one that we would look at the first. Heavy metals and PAHs need to be looked at. Here's some data, and I'll use some of these slides just as token prompts for making a point. We need to look at PAHs and dioxins because they are generated through pyrolysis, or can be generated by pyrolysis. The good news so far is, I think we've in most, if not all, slow pyrolysis biochars, we're way below any concerns. In fact, way below composts and manures, uncharted manures. But that is something that one has to test for sure. Heavy metals are a different story, because heavy metal in means heavy metal out, although there are important nuances in terms of their availability. They're not generated or destroyed. PAHs, organic chemicals, are different. Sorry, I should point out that there's several guidelines. The International Biochar Initiative, which means all of you in the room, have generated a document that outlines these thresholds, and it goes to continuous revision. We'll see a new version come out soon. Now I want to mention a few other effects of biochars that are not in any of the classification systems and not even thought about how to incorporate them, but are an entry point and an interest of many users and scientists to explore, because they're quite intriguing. Nutrient leaching, effects on nutrient leaching is one of them. This is a study from David Laird showing the leaching of phosphate after manure additions with different biochar additions. Without biochar, there's no leaching. These are the open symbols. Without manure, there's no leaching of phosphorus, or very little leaching of phosphorus. The open symbols. When we add manure, we get a huge spike in phosphate leaching in this laboratory experiment. But if we add more and more biochar, that leaching goes significantly down, and we'll see those results consistently. But how do we capture those? Which biochars are doing this? This is the one biochar being tested. Are all doing that? How do we put that in a classification system? What is nitrogen doing? And it's more nuanced, because it's not just absorption reaction. What about other loss mechanisms, such as erosion? Might they be accelerated? Very little on erosion, and the effect of biochar erosion on nutrient buffers. Another aspect is the absorption of heavy metals, such as copper, and its toxicity. We see that in fresh biochars, and that seems to hold for many types of biochars, but not all biochars, but many types of biochars show quite a bit of absorption, shown here on the y-axis, with greater copper concentration. So biochar seems to absorb quite vigorously copper, and several biochars have shown that. And that means any toxicity that we see here, full death of the plants with increasing copper additions, is alleviated when we add more biochar. You see 0% biochar, 2%, 4% biochar. At high biochar concentrations, we see no effect of copper on the reduction of plant growth. So some negative effects of heavy metals may be alleviated by biochar, by this type of biochar. Are they all? How long does it last, and is it economical? Lots of questions still. Organochemicals. Herbicide leaching seems to be reduced by some of the biochars tested. I'm sure it's not all biochars. This is a study of one biochar looking at the atrazine concentrations in shallow groundwater after biochar additions in comparison to no biochar additions. Control here with biochar and acidified biochar. You see the concentrations in the shallow groundwater of atrazine go down, and the atrazine extracted from the soil goes up, so more stays in the topsoil, less is leached, which is a good thing. What does the atrazine do up there? Is that a bad thing or not? How do we capture the ability of certain biochar types to performing that or not? Those are questions, and then putting that into a classification and guidelines framework. One of the questions is also, if we have absorbed that atrazine and reduced leaching of atrazine into the groundwater, the absorption of atrazine may also reduce the efficacy of the atrazine to control herbicides. And you see here that with larger biochar additions, this is no biochar, this is the large biochar additions, we need more atrazine to control our weeds. So by reducing atrazine leaching, are we buying ourselves the need to add more biochar? Or can we, this is again only one biochar, can we develop biochars that don't do that? And does it do that for long? We don't know that either. So that's definitely something to look at. Denitrification is one of those effects that could potentially have a huge benefit, because it's not a one-off carbon sequestration benefit at production, but it incurs a reduction potentially over long periods of time. But does it? We don't know at this point. What we are relatively sure is that we should give this a look, because we have now more and more studies that look across a large number of, fairly large number of soils, a reduction in N2O that is rooted in a true reduction of denitrification, but we don't really know for how long it does so. We know it does it for several years, it doesn't do it very long. That would make a huge difference to the greenhouse gas patches, even if we can never capture those and monetize those, because it might be too variable. Biochar effects on soil biota. I know that a lot of people in the organic community are very interested in. You see this famous photo, thanks to Dr. Ogawa, who is here at this conference also, who took this photo almost decades ago. So this is not new. These photos of showing showing occupation and exploration of microorganisms of biochar pores. These are biochar pores where these hyphae go in. You see hyphae smeared all over. You see bacteria exploring the biochar pores, but we still don't have peer-reviewed literature that shows that this is a greater proliferation inside the biochar than outside the biochar, whether this has anything to do with the surfaces, what the mechanisms are. But this can be important because we have also these kind of results that we don't really know where they come from. This is an Israeli group that shows, has worked quite extensively and continues to work on disease severity. Here, gray mold on tomato, but they showed other diseases and other crops, and shows that the disease severity after infection. And you see with greater biochar addition 0, 3, 5, disease severity goes significantly down. Mechanisms in their own paper, they have some speculation, but they don't really know. Do microorganisms have something to do with it in the rhizosphere or not? Other diseases that are soil-borne might have some direct interactions, have have some signaling effects that can be invoked. But that's an area ripe for exploration that needs to be caught up. We see a lot of products today, and that's really a change from 2 years ago. Even last year it was nascent. This year there are a lot of products in the marketplace. There are companies, most of them I guess are starting, have still a limited track record. What do we know about those products? If we don't have a classification system, if we don't have the guidance that I showed before, what is the consumer buying here? What are the heavy metal and pH contents in those? I think the work that's happening now between the producers and the academic community on the platform of the regional, the national, and the international biochar initiatives are critical to overcoming these constraints. And I'm really delighted that the different sectors are coming together in these conferences such as this one, which is really critical, the communication, to keep that open. Even though I understand that a lot of scientific colleagues are now more and more dragged towards the scientific conferences, it's important that we still interact on this level to provide guidance. These provide, of course, the opportunities that they are tailored to specific needs, and then we exclude a whole host of the issues that I described earlier, because we can do the testing, we can provide the labels, the guidance. This should be used for this and that purpose, and provide assurance that it will work for that. So beyond material, very, very briefly, there are trade-offs between gaseous fuels production, liquid fuel production, and the biochar production. The more biochar we produce, the less fuels we produce. So you see the curves go all down. With more biochar produced, we produce fewer fuels, and the curves have different shapes and different y-axis here, depending on what kind of fuels, whether gaseous fuels, liquid fuels, and what, whether it's synthetic gas, whether it's methane, whether it's ethanol, butanol, or Fischer-Tropsch liquids, and we'll need to recognize that. Just a couple more slides. Going forward, what kind of scales are we recommending or do we see emerging that have certain attributes? Here you see the rate of application, whether it's just 1 kilogram per hectare per application or 100 tons. We might have systems that use just very little. As an inoculant carrier, you probably apply minute amounts. As a component of fertilizer, and in a mixture to regular fertilizer application, you might just apply tens of kilograms. But you apply them probably every year. So in 100 years, you apply them every year. Whereas as a potting mix, you apply probably up to 50, 80, 100% biochar, and use every year. Whereas for remediation or carbon sequestration, you might apply a bit more, or even for carbon sequestration, quite a bit more, in the tens of tons per hectare, but you apply it only once or twice per 100 years. So you see again the scale and the system, that there are great interactions between those. And again, there is no one biochar system, as there was no one biochar material. Scale of biochar production might have also something to do with the entry points. And you see here, maybe at the very low scale of application where we have an inoculant carrier, we really don't generate energy. We just want to produce biochar. There's no waste management. We use good material to do it. We produce minute amounts because the company really needs minute amounts. Cook stoves, we might be interested in biochar, but maybe the major interest is in energy generation. And so we have already more value, more products that come out of the system. Maybe fertilizer management, we're not generating energy, and we're just interested in in carbon sequestration a little bit, but mainly in biochar, biochar production. And then with larger scales, maybe we have more value, more products, a more diverse set of products that can be generated. So the scale will look at, will probably trigger very, very different systems. And just the last couple of slides, biochar and soil science education. I found it interesting that there are a lot of high school students, but also college students are interested in this area. Certainly the public is interested. And I think we're not at the end of looking for quote-unquote solutions. The word solution doesn't go over really very well with a lot in the academic world because we don't believe in blanket solutions, but as in a toolbox of different solution packages. But definitely it seems that biochar and other technologies can contribute to excite the new generation to look at that. Here from Canada, I'm introducing Biochap here, an educational video that was made, so showing that this seems to be interesting for education as well, looking at new ways of doing it that you hadn't thought about before. Biochar exploring the Amazon, Biochar holding water and nutrients and carbon in the soil, doing all kinds of cool things. And dancing and singing. So where to from here? Definitely, biochar doesn't fix our well. There will be many situations in soil constraints where there is no need for biochar. We need to find appropriate places for biochar systems and management. We need to develop these knowledge systems, and there's really no single biochar. So maybe we should only talk in plural, and there's no single biochar system. And how fast is this going to happen? Who knows? This is the Model T, and the Model T was Model T because they started at A. And this was what it looked like. So it takes a while, but that's good to do the due diligence in this area. Thank you very much.